Good afternoon. Thank you all for coming again. The third installment of this year's lecture series. I think, I don't know what you think, but I think it's great. I've been here at the University of Arizona since 1983, and one of the things that I find extraordinary is that I'm surrounded by colleagues that are driven by passion in doing science, which is most of the folks that I'm in touch with, but also for making a difference in the community that they live. And I think that it shows with a connection that has happened with all of you. So making a difference is important. One of the people that, for example, to give you a sense of how serious this is taken, is the first speaker that you heard, Stephen Kubarov. We were having a beer the other day, and I was telling him how good his talk was. And he said, well, it just took me 3 months to put together. That's the kind of commitment that you see from my fellow colleagues here in the college, and it shows in spades. But I'd like to introduce you to another gentleman, which I am just honored to be a colleague with, John Pollard. He's in the Department of Chemistry. He's a professor of chemistry. And he also plays a part in today's operation in a way that he'll describe right now. John?
Thank you, Joaquin. Well, as I know all of you are probably aware of, the state of Arizona isn't exactly extremely supportive of K-12 education. We've raced to the bottom in this area, but I can tell you that the College of Science in many ways has tried to help with this by providing support for our local teachers in many ways. One of the ways is a program that we work on here associated with the College of Science lecture series, where I teach a course for local K-12 teachers. All of them are here, and I'd like them to stand up if they could. There's about a dozen of them here. Come on, stand up, stand up. Yeah. Thank you. As you can imagine, this is not an easy job. And the goal here is we, through the support from the Galileo Circle, by the way, these teachers take a course, this course, where they attend the lecture series. After the lecture series, we get to bring the speaker back, they're not done, to a undisclosed location on campus for a small QA session for about 45 minutes. And the goal here is not only to provide continuing education for these great educators, but also to look for ways to contextualize the things that they do in the classroom with the content of the lecture series. It's something we've been doing for a number of years, and it's really a great way to take content directly from our great researchers here at the University of Arizona and translate it straight into our classrooms. In addition, by the way, I also have another class that's here. I have two classes here of 18 honors students who are first-year honors students taking an honors colloquium. They are also going to join us tonight for the QA session. So I have about 30 people there. And then also some of the teachers have some high school students who join us. So the teacher or the lecturer comes back for a Q&A session with teachers, freshmen here at the U of A from the Honors College, and high school students. And it's quite a time. They definitely get grilled in a good way. So I just want to acknowledge the great teachers, of course the honors students, and thank the support from the Galileo Circle for supporting that program. Thanks.
Let me now continue the thanks, and the sponsors of the title sponsors of the lecture series are the UA Research Discovery and Innovation. That's our Vice President for Research. Tucson Electric Power and Roche. They've been with us since the very beginning with a fair amount of cash for all this. And then the underwriters who are Accelerate Diagnostics, Arizona Daily Star, Canyon Ranch, which is a brand new underwriter. Thanks so much. Cox Communication. As John mentioned, the Galileo Circle, which are the members of our community that strongly support the college. Godad Design, it's all these beautiful designs that you see here. Godad is the one that does that. Halua Loa Company, Marshall Foundation, Wynn and Tarbet Patent Law, Raytheon, Research Corporation for Science Advancement, and Tech Launch Arizona. And please help me thank all these people. In the previous lectures, we've heard about what machine learning is all about, what artificial intelligence is all about. And today, Nirav Merchant is going to tell us a little bit about how you actually put together what you've learned in the first two lectures in a very creative way. He is director of the UA Data Science here at the University of Arizona. He received his undergraduate degree in industrial engineering from the University of Pune in India, and he's a graduate degree from the U of A Systems and Industrial Engineering. A few highlights would include when commercial robots became available in the year 2000, along with Mike Hammer and Matt Kaplan, maybe some of you know him, he established the first and largest automated human DNA genotyping facility at the U of A. Now, what that means is whomever has taken one of these things from the National Geographic to figure out if you came out of Africa, actually Nirav was the one that put it all together. So he also, with the arrival of smartphones during the mid-2000s, he collaborated with other folks to develop the first USDA-funded smartphone-based health intervention platform. And in 2006, along with other U of A colleagues, he led the technology team establishing the first and largest NSF-funded CyberInfrastructure grant in the country. At that point, there was, I think, $60 million, and NSF had not written a larger proposal, given a larger amount of money to anybody for this kind of operation. At the point when he did it, it was called iPlant. Now it's called Cyverse. They're using one bad word for another one. But anyway, what they do is pretty good. So please welcome Nirav Merchant.
Thank you, Dean Ruiz, for the kind introduction, and thank you all for being here. It's my honor and privilege to be part of this lecture series. So before I begin, a question that was asked to me, am I used to being around a large crowd? So my colleagues who've done this before said, when you see a large crowd, it's different. Have you done this before? Have you been around a crowd? At which point I said, when in my life have I been around with like a few thousand people in close proximity? And then the thought that came to me was, well, I grew up in India. And then every day I took a train from home to Bombay Central. And that train has a capacity of 3,000. Takes about 15 minutes from home to get to Bombay Central. So to feel more comfortable in my skin, I'm going to visualize all of you guys with me taking a journey to Bombay Central in a train, and I hope the train arrives in 15 minutes, because that's what we're given. And what is going to happen is you guys are going to be comfortably seated, and I'm going to be the only standing passenger. Both of those things never happen in a train in India. So with that, I'll begin. So the question is, working alongside thinking machines, what is a thinking machine? And so you heard from Stefan when he spoke of Alan Turing and his paper, where he asked the question, do machines really think? Well, I am not going to bring Alan Turing or even Heidegger to this conversation and sort of make it more complex. I'm taking a much more relaxed, casual view and understanding of thinking machines, and I'm going to explain how. So if you see these are from 1950s, where our desire for thinking machines has always been there. Here is UNIVAC trying to tell you that you are dividing by zero, hence you have the error. They're trying to think for you, and even Apple, okay? Think different. So let's take a look at what is a thinking machine and what is my definition of thinking machine. And to easily put that in context, I decided maybe a good way to look at that is thinking of cruise control. We have cruise control in our car. We use it when we need it, usually on a freeway. And the way we utilize it, we achieve the speed that we need. And once we hit that speed, we press a button and we are maintaining that speed. Whether the road is going up or down, it does maintain that. But at the same time, if your luck is anything like mine, the moment you set that, somebody's going to come in front of you, slow down, and you have to hit the brakes, and you lose cruise control. But today, when you start looking at cars, much like what you see in this image here, They come with adaptive cruise control. What does that mean? You look at the car ahead of you, you set up the speed, and you say, I want to maintain a safe distance. And you can see in this car, this is a real car, where it sees the car, not just the one in front of it, but two others that are in front of it, and it maintains the distance. So now, when you're on cruise control, you don't have to think about, oh, this person's stopping. The car not only maintains the speed, but it starts slowing down, and it'll even come to a complete halt without you having to do anything. The difference is, in the regular cruise control, the only thing in your body that got a brake was your leg. It was not having to use the gas pedal. But in this cruise control, in the adaptive cruise control, your brain is also allowed to relax a bit, because now it's not thinking about, oh, something is breaking, I need to stop. Now, there is a trust factor. If you don't trust this automation, yes, your brain's going to be freaked out all the time, but it comes to a point where the cognition overload goes down, and you are comfortable with this automation, and some of the thinking it's doing for you on its behalf. And so that is the kind of thinking machines I'm talking about. So we are in a very interesting relationship between machines. You heard from Stefan about the algorithms. You heard from Mihai about algorithms and artificial intelligence. More importantly, the intelligence augmentation. And that's the camp I sort of subscribe to. And Mihai hinted on some of the data elements of it. I'm going to talk a lot more about data and the human aspects of it, and why it's really critical for us to be really comfortable with machines, with data, and more importantly, have a platform that allows us to bring all of this together, the substrate that allows us to connect the algorithms, the machines, the systems, and the human beings that help it do what it needs to do. And so with that, I will talk about data. So the data we produce, we're really good at it. How good are we? And sometimes people underestimate our capabilities. So first, let's understand who is online. So if you look at it, we are about 7.5 billion people. 3.7 billion are already on the internet, which is a staggering number. 2.7 are on social media, and I know that's not a good number, but still they are. And then you have 5 billion, close to 5 billion mobile phones, 5 billion mobile phones, and half of that, 2.5 billion, are on social media using their phone. So you can easily assume that there are 2.5 billion phones in the world that are on the internet, which is, again, an amazing number. So what kind of damage can these people do when they start spewing data? So let's take a look. So what is a minute on the internet? How much data can we produce in a minute on the internet? So you're going to find your favorite rectangle, and your eyes are going to go for it. But the first one is 87,000 hours. 87,000 hours of Netflix video is streamed every minute. And the question you ask, how can you get 87,000 hours in a minute? Well, when you have 5.5 million people trying to watch something, you get 87,000 hours of video in a minute. 4 million searches on Google, 2 million phone calls or connections or voice calls on Skype, 168 million emails, 350,000 tweets, and I know we can attribute that to a few people. And so you can start seeing that we are very active online. And so I'm going to let this run through and find your favorite rectangle. 13,000 apps downloaded every minute. So you can see we have lots of people, and they're really busy. Okay? So before we decide and explain what it means to consume that data, we need to explain a kilobyte, and I know the purists in the room will say that's 1024 and not 1,000, but 1,000 looks better on the slide. Trust me, it aligns better. So 1 kilobyte is 1,000 bytes. 1 megabyte is 1,000 kilobytes. 1 gigabyte is 1,000 megabytes. So far, most of you sort of dealt with this. Some of you have heard of terabytes and even possibly consumed terabytes, which is 1,000 gigabytes. Well, in my world now, a petabyte is a common number, so it's 1,000 terabytes. Okay? And so now that you know what a petabyte is, This is what the US generates in 1 minute on the internet, 2.6 petabytes every minute. So those of you thinking that all the data online is always saved, use this number and count how many hard drives that would take. So if somebody is telling you everything is saved all the time, there aren't that many hard drives in the world produced that could save that much data all the time. But yet, the population is producing this data at such a staggering rate. And that is also happening in science. So for those of you who are familiar with LSST, has its roots here, it's going to produce 15 terabytes every night for the next 10 years once it's commissioned. Right in the middle is the world's largest robot for imaging in the field right here at the University of Arizona in Maricopa. That white box that you see goes up and down the field on the rails 24 hours a day and night, capturing data about the plant that's growing, everything, every little movement, every little reflection of sunlight, radiation on it. It knows about it, and it's capturing it constantly. And 8 terabytes is a conservative number. The more sensors you can put on it, it'll capture more. So you can almost think of it as LSST is looking up, gathering a lot of data. This thing is looking down, gathering a lot of data. And then finally is the genomic sequencers. This is where you start sequencing genomes. Here is NovaSeq from Illumina. Their goal is to sequence a whole human genome in an hour for $100. The whole genome in an hour for $100. The same thing 3 years ago, the goal was $1,000, 3 days. 10 years ago, it was millions of dollars and took them a decade for about 3 or 4 of them. So you can see where we have come from a decade and millions of dollars to an hour and $100. But the amount of data that we are gathering is massive. Again, this is 9 terabytes in a day. So all of this is constantly producing data. And what we sort of don't pay attention to is ourselves. We are now going to become the biggest producer of data, and we're slowly moving towards that. So here is an example of Internet of Things, and I'll explain what that means. We all have phones. I talked about the phones getting a lot of data and streaming it, good enough. But then on your phone, you have a few dozen sensors, whether it's your location and GPS, it is the steps you take. But then people go ahead and get special sensors. Here you can see an example of a person having a heart rate monitor on their wrist. And all of this data is going to the cloud. Similarly, your house, you have your thermostat that is sending data, your meter, electricity meter, and if you have solar panels on your roof, everything is sending data somewhere. And then you typically have someone who can make sense of that data and do something meaningful from it. Now, here your physician or your healthcare provider is looking at your heart rate and the steps you took and say, well, you're doing good and you're keeping up with your fitness, good for you. Or it might be your coach or someone else. But the Internet of Things is putting all the sensors online, and we are now constantly streaming activities from anything we have that we own. So some of you may recollect Stefan, in his talk, complained that his toaster had become a black box and he could no longer fix it. For those of you who can actually sort of relate to this, of all the devices getting online, it is rather painful to have to worry about the security of your device. And here you see this couple trying to buy a toaster, and then somebody's trying to sell them a firewall, and the firewall prevents bad people from getting into your toaster. So, okay? Now, if you don't fall for this upsell, you may end up with something like this, where so you have to be prepared for the consequences of having a life where you are on the Internet of Things, okay? And that's reality for us. So now let's take a look at what can you do with this data that you're gathering at this sort of staggering and amazing pace. So the goal is to convert this data into something more meaningful. So the most base layer of this pyramid is raw data. If you just start spewing data and sending it somewhere, and it's just getting collected, It's sitting there. It doesn't really have much value to it because it is not transformed into anything that's meaningful. And by that, what I mean is it has to go through some processing before it becomes useful and becomes information. Okay? So just becoming a data pack rat doesn't really buy you anything. Okay? You have to do some layer of processing before it becomes useful for you and it becomes information. The layer above that, once you apply some cognition to it, you can transform that information into knowledge. And eventually, when you start applying judgment to it, you start getting it into wisdom. So you really want to take your data, get more insights out of it, and keep going up the pyramid. The example I can give you is from Mihai's talk. If you remember, in the last talk, Mihai mentioned that he had hundreds and thousands of papers, scientific papers, literature, that he gathered, and then they processed them, and they were able to extract pathways from it. Now, when they did that processing, the papers by themselves were raw data, but the moment they moved it on and processed it, it became information. Okay? Good enough, they understood the pathways. When they applied cognition to it, and they said, well, these are pathways that were never really discussed before, and they seem to be related to breast cancer. That's when that cognition moved it into knowledge. Now, from going from knowledge to wisdom, there's a lot more experiment and other things that need to happen. But the point is, going from data all the way to wisdom, there is different levels of processing, and there's different level of expertise that's required. And a lot of what you see is at the data and information layer, because that is currently very well understood. People can really process those things well. As you move to the upper levels of this pyramid, you start relying on systems that are much more driven by machine intelligence, and that's where you need the machine learning and artificial intelligence and intelligence augmentation to solve it. Okay? So keep this pyramid in mind. We are going to revisit that multiple times. So how does regular data become big data? Okay? You keep hearing the word big data, and you're going to hear a little bit, or maybe a lot more about it in a few weeks in a talk when Win talks about possibly there not being big data, which I sort of subscribe to. So how does regular data become big data? Okay? Welcome, my friend, Big Data from Stefan's talk. We love him, so we bring him from time to time. For somebody who opens a file and it crashes Excel, that file is big data for them. Okay? But jokes aside, big data as a concept is pretty amazing. There's a lot of marketing hype that got around it. But the core concept that I want you to take home today is there are two flavors of data that it deals with. First, called structured. Think of it like a spreadsheet, where you have columns, but each column, you know that this is date, this is the name of a person, and so it's pretty well described, and there's lots of data in it. And then there is unstructured data, which is just like web pages. You can have text anywhere. It could be a paper, literature, where there is no structure, but there's a lot of text to it, and it's very hard to interpret that. You have to read the whole thing to make sense. So now you have structured and unstructured data, but inside that are patterns. And there is no exact relationship between those two. By that, what I mean is, in your spreadsheet might be social security numbers, but there might be no social security number here. It might be a person's name. Can you link them together? And you might, as a human, say, oh yeah, you can look up the person's name, but then their name is different, and it's also an alias, and all those things start coming in the way. But if you rely on some of the techniques that come from big data, where the underlying machine learning methods allow you to make these connections much more easily, that's when you start taking these patterns and being able to predict and do good and useful things with big data. Okay? And you always have the large volume and velocity and variety. Those are nice, cool marketing things. But keep in mind the two things: structured, unstructured, and lots of patterns. And as you can see, this young gentleman is trying to get out of his homework, calling it big data homework. So let's see how we can take a simple question that I have, or I had, and convert that into big data very quickly. So I was interested in knowing how much solar radiation is on my roof, is my house a good candidate for getting solar panels? And much like any reasonable human being would do, I go to Google and type it in and say, solar panel roof calculation. And needless to say, Google, the first hit, which always surprised me, was a Google project. And I'm like, oh, OK. Maybe I should go check Google Project Sunroof. I didn't even know it existed, but Google suggested that I should look at it. So I looked at it and then said, oh, you just enter your home address and you can check for my roof. So I did that, ta-da, and there's my house. It figured out the boundaries of my house. It even figured out there are trees that are casting a shadow, so which part of the house would be a good candidate for putting these panels, and how much savings I could have if I get the solar panels, which was pretty nice. It's a simple question I asked, and Google did all the hard work for me and gave me an answer. And then if you are, let's say, from the county or you're a local government official and you ask the question, what's the potential for the zip code 85704 if everybody got solar panels? You can ask that question, but now it has to calculate that for every house in the zip code, do all the calculations. But it very readily could do that, and I was like, wow, this is brilliant. So I asked a question about my house, my zip code, even the whole of Tucson, even the whole of Arizona, and all these numbers were just sort of flowing. I got really excited. I said, OK, let's find out. So I read the frequently asked questions, and then Google explains what they do. So they have a list of known addresses, much like how they found my address. There is satellite imagery that they have, weather data, all of which you can get readily. And then they go ahead and extract the roof outline from the satellite imagery. There is a very standard calculation for shade. And then there is a government project, the National Renewable Energy Lab. They give you a very simple lookup table for photovoltaic and the cost. And you just, how much area do you have, multiply by it, and boom, you have all the numbers. I'm like, that's really nice. I should tell more people about it. And of course, the people I hang out with do interesting work. So the person I talk to, they work, they understand, and trying to get some bearings on how a forest grows and shrinks, and how trees grow on certain hill slopes better than others. And they keep performing these solar calculations. And I'm like, guys, you should check this out in Google, and it's all there. And we should just look into it. Maybe that's the answer to the troubles, and every time you ask me questions about how do we do this in a bigger scale, maybe we should rely on Google. So we put Santa Catalina Mountains, that's where they do their research, boom. Google doesn't have it. And to be fair to Google, it wasn't designed for that, right? They designed it for urban areas, that's their interest. They can monetize some of it. They don't care about the Santa Catalinas. And if you want to go to them and say, hey, Google, can you maybe look on this side and also use this? Their calculators are based on finding a very clear edge of a house and a shape. They're not going to look at a mountain and little trees and shrubs, and they're not going to give you the numbers that you want. And this is the reason in science we have to build certain platforms on our own, because what you get in the commercial world is close, but is never really the right there for you. So you pretty much, sometimes you feel you're reinventing the wheel, but you're not, because there isn't an option. So this is what happened with Google. So I told my colleague, oh, but they've listed all the sources, and you should just be able to take all of that and do interesting things with it. And there's open source data. We all hear about it, open data, OpenGov. So here's a site where you can get open data, and it's easy to share and get, and look at data.gov. There's agriculture, there's climate, ecosystems, energy. All of this is available. And then we found something called open topography. It shows you all the 3D mountains everywhere in the US at very high resolution. It's like perfect. We found the source for Santa Catalina, and we can now start doing some of the calculations. And then we found the source for weather. It's right at Oak Ridge National Labs. There's something called DayMet. They have temperature, precipitation, all sorts of interesting data for every square inch in the US, anywhere in the US. So this is perfect. You found your data sources, but then you don't have enough people who can analyze and extract value. The moment you ask them, does anybody know how to work with this? Meh, no. I know where the website is. That's about it. And so that doesn't help. And then you're like, fine, we have the data. Let's go get software. We'll figure something out. So here is open source software. So there's open data. There's open source software. And we found this beautiful piece of software called GIS. It's Geographical Information System. And it even has a beautiful calculator for solar irradiation. And it's way more feature-rich than what Google could even offer. It's like, this is brilliant. But there aren't any people who can connect those algorithms to the data and put this together. So when you start asking someone, hey, can you take GIS, take some data from DayMat, and then go to open topography? There's no one who knows how to do that. And that's sort of strange. So then the question starts emerging, even if I could put all of this together, where should I run this? Okay? Where is the place where I can get compute cycles? Okay? This question comes up, do I need to know programming? And the answer is always yes. Okay? Will it scale for a large area? I want to do it beyond Santa Catalina. Can I share the results with other people, with other communities? Can others verify my results with their data? Who improves the solar model if we find something new? And finally, the most important one, can't I just have someone build this and perform all the analysis for me? Everybody wants this unicorn. Like, right? Every professor that you ask, they're hoping to find a student in their lab who can just do this for them, right? And so this is what happens, okay? So when you put an ad out for a student and you say, I want all of this, this is what happens to the poor student, to be fair to them, okay? So far we've talked of machines, the algorithms and data. We talked of DayMat and all the places. We talked of GIS. Now let's talk of humans. I mentioned multiple times, there aren't enough people who know this. There is a lack in training. How do we fix that? And where do we go run this? So I would like to talk about Jim Gray and his work. Jim Gray was an amazing computer scientist. What he said was, we are in the fourth paradigm of science, the first one being empirical, where thousands of years ago, then we came into the sort of theoretical phase, and then the last few decades have been computational, where we do simulations and modeling. Now we are in the data exploration phase, and you can relate to that because the amount of data that I showed you that's flowing through all needs data exploration, and the question for the solar model is exactly the same, okay? But Jim said something extremely important, which was the speed at which any given scientific discipline advances will depend on how well its researchers collaborate with one another, but more importantly, one another and technologists. Every discipline, it doesn't matter what, whether you're in astronomy, in geology, in computer science, in plant sciences, you have to collaborate with technologists to get the best bang for the buck from your data, okay? So what happens when you try and get a domain scientist and a computational scientist? First, I'll try and explain to you what a domain scientist is. Domain scientists are experts at gathering data. They come from disciplines like oceanography, field biology. These are extremely hardworking people. You do not want to underestimate the effort that they put in to spend months in the field painstakingly gathering data, often risking their lives to do that. But they are gurus at gathering data, okay? The computational scientists are the computer science, information science, the mathematicians, the engineers, okay? Now, I'm not trying to say their jobs are, cushy and they don't have to worry about it. They have hazards in their jobs too, but these two groups are pretty far apart when it comes to collaborating. Okay? And it's not that they don't like each other, they don't like to socialize with each other. They absolutely do it. What happens is the friction at the boundary of infrastructure when it comes to sharing data, sharing compute, is what prevents them from collaborating together, and I'll explain that further. So what we really need is for these groups to start sort of having much more active dialogue. And that happens when the person who's designing the computation says, hey, I have a method that would work with your data set. Can you give me something? What does the domain scientist do? Find the nicest, cleanest one, polish it, and say, here's my data. And the person like runs it, and wow, good results, awesome. So they tell the person, yes, it works. And then the moment the domain scientist understands that, they pull up a big truck full of data and give it to this person. The computational person raises their hand and says, whoa, that's way too much data. I can't handle this. I'm just going to give you my method. You run it at your place. And that's when the domain scientist says, hey, I don't do those things. So now you have two groups that absolutely need to work together, but they are now fighting over the boundaries of infrastructure. And that's sort of the part we need to change. And the way we can change that is having a nice overlap where each of these groups have some, let's say, empathy for each other's work and understand the limitations of technology, and then they can together build infrastructure that is relevant for their research. And that infrastructure often is called cyber infrastructure. And let's talk a bit about it. Okay? I'm going to take you back in time, 2009, February 9th, this very stage, this very event. Maybe some of you recognize my colleague, Vicki Chandler. She spoke to you about a project called iPlan Collaborative, where National Science Foundation, as Dean Ruiz mentioned, realized that they were funding a lot of data gathering, but not enough of what they were funding in the computational sciences was coming over as a solution for the plant science community. And they figured we had to rethink this question in a very different way. And so that was the birth of our project. So Vicki, on this very stage, talked about how scientists, teachers, and students will develop an infrastructure that allows and empowers advances in plant biology. And what I would like to do today is show you where we took this project and where we are today and where we are going in the future. So this is sort of a quick timeline of what we did. We were sort of born in 2008. In 2010 is what our public launch was, where we went to the community and said, here's something, start using it. You would wonder what we did for 2 years. Good question. What we did for 2 years is go and talk to both of those circles that I talked about in the Venn diagram that doesn't overlap, and ask them, what is it that's preventing you from doing a collaborative research project with somebody in the computational sciences? And the more we talked, the more we learned, we realized that there were fundamental gaps in usability. There was a complete lack of training, and we had to fix those. None of those sound really sexy to get funding from NSF, but we were focusing on grand challenges, but there were so many challenges that had nothing that were grand. They were like straight up, oh my God, we can't do this. So people were producing data and shipping hard drives. How can you collaborate on a multi-terabyte project where FedEx and UPS is part of your research cycle? You can imagine what happens when you send something and it disappears or appears after a few days, and by the time it reaches at the other end, you've already changed something. So are you just constantly going to be shipping things around? That's not the way to do science. And so that's what we did, and then our mission became design, deploy, and expand national cyber infrastructure for life science research and train scientists in its use. Emphasis on train. We had to make sure we were training people. And so in 2013 is when our mission was expanded from just plant biology, because everything that we had built was so generic that anybody in life sciences could use. And I'll show you what we built. And in 2016 is when we realized that our astronomer friends, our engineers, the hydrologists, they all were showing up in our infrastructure doing cool things. And the name iPlant was rather confusing for them because, hey, why are you in plant cyber infrastructure when you're doing geology or you're an astronomer? And so it was really easy for us to solve that problem by changing our name from iPlant to Cybers, which means cyber universe. Anybody come, do good things using our infrastructure. And we changed also our tagline to transforming science through data-driven discovery, much like what Jim Gray said in the fourth paradigm. data-driven discovery, so the data exploration was at the center of what we do. So now when I say cyber infrastructure, what comes to people's mind? And this has always been the case. You are a big audience, so I'm not going to poll each of you. But for most people, it is lots of machines, rows and rows of computers, fast networks, visualization. Very rarely do they say humans. And humans are the most important part of cyber infrastructure. If you don't have the right people who can teach you how to use this and answer your questions at the right time, most likely you are not going to use this expensive piece of equipment, and even if you use it, you are going to use it very inefficiently. So having a human in the loop, and I want you to keep this in mind as the talk progresses, human in the loop is most important for any of the machines that think. Okay? I don't want you to pay attention to any text in this, trust me. Okay? All I want you to pay attention is right here. At the top layer are things that we call products. They're ready-to-use things. Okay? If you remember the solar question I had about my roof, that would be someone like me coming at the top level and saying, all I need to know is how much solar radiation is on my roof. I don't care what's below this, don't care. I just have this question, and I start there. But the moment I start asking questions about Santa Catalina Mountains, and can I do this, can I change that, can I give you a new model, all of a sudden I am migrating on this technology stack and coming closer to the systems that I can then control the levers on. I can answer my own question. And that's important because when you're at the top layer, the flexibility is not much. It's like, give me your address, I'll give you an answer. If you put in a Santa Catalina, I'm just going to say, go away. Well, when you're doing research, you don't have that choice. You have to figure out how to get those numbers. And so this is very common for our users to say, all I need is this, and then after about a few days, but it would be nice if it also did that, and can it do other things? And so that's sort of how our users graduate into coming closer to the system and building their thinking machines. Okay? The other piece that I would like you to draw attention is right in the middle. Don't try and read anything. Just right. That's our foundation, where what we did is just like how we went to the community, asking questions about what was preventing them from collaborating. We went to groups that were doing this for 20, 25 years and doing an amazing job. For example, IRODS was being used by the astronomers. Condor was being used by the LHC, which you heard last year. All of these projects have been doing this for a long time, and they had a lot of experience. So we went to them and said, this is what our community is trying to do. This is what you guys are doing for particle physics. Can we fill this gap? And all of them follow the open source philosophy. So their code was open. We made changes. They made changes. And they all welcomed us with open arms. And we were able to make that modification and do new things very quickly because all of us were subscribing to the do not reinvent the wheel philosophy. And so we were up and running very quickly, and this blueprint that you see as our technology stack today is used around the world in multiple projects. And now we have Cyverse UK, there is Cyverse Africa coming together, Cyverse Chile, Cyverse Brazil, Cyverse Australia. And so all of these are taking these same templates, the same tools, and putting together their own solution. And that's really important. So how is the growth for us over time? So labs, data, analysis, people, that sort of is the theme. And then labs usually that have funding in countries where it's easy for them to generate data. They produce the data, they use high-powered systems that we provide, and then it's accessed by people worldwide. If someone is doing research in Australia for the same plant and the same condition and producing some data, why should I be reinventing the wheel? Can I not just collaborate with them? And this is sort of the growth, and I'll show you where that comes from. But we have about 1,600 non-academic institutions, 3,735 academic institutions, and 51,000 registered users. Now, a point to note here is that these academic institutions are not research one only. They're not big universities. These are small community colleges. These are researchers who, let's say, graduated from U of A and are now teaching at a community college. typically they had to scale down the research question they wanted to teach with because there was no computational infrastructure. We democratized that infrastructure for them, where now they can go and teach their students real scale data. And that's important because real data is ugly and hard. Toy data, polished data, very easy to work with. And then when you go into the real world and try to do real research, that's when you realize, oh my God, my teacher duped me. They all just made it sound so beautiful and easy. It is extremely hard and ugly, okay? And so this is what we have done for our community. This is slow months of summer for us, and what I would like to point out is on the left-hand side, you're seeing the number of terabytes that go in and out. So in 62 days, half a petabyte of data flowed through the U of A. The same very room that you're sitting, the cables that go below, carried half a petabyte of data in these 62 days. So you can imagine the activity that happens. And if you look at the total amount of data, the max daily, 5 terabytes upload, 46 terabytes download. Remember when I showed you the LSST? That produces 15 terabytes a night, right? We have 3 times that data going out from our project today. And this is done by our users who are biologists, who have no IT support, and they can themselves manage terabyte scale data. And that's where we need to take our community through CyberInfrastructure. And so this is the reality for most of our users. If we don't empower them to use the right tools, the right techniques, and we train them, and when I say users, I mean all of you. There's nothing in our infrastructure that prevents a citizen scientist from doing an awesome project, which we have quite a few of them. And so that sort of is me standing. I've seen what the hydrant looks like, and it's scary, but here are the researchers who just say, give me a glass full of water, please. It's like, no, there is no glass. Once we open this, you better know how to deal with the flow that comes out. Okay? So what do users do with it? Okay? Astronomers who are looking for exoplanets can now analyze in few hours something that took them days. We recently had 100 oceanographers, my colleague at UFA, Joel and Russell, who you heard a few sessions ago, gathered 50 people in person, 50 online, and they all got together and improved their models, and they weren't fighting about where's the data, where is it going to run. Their focus was on the science. Okay? Scientists from 3 countries, they shared their expertise, and they validated a new cancer therapy. Teams analyzed thousands of complex genomes in few days instead of few months. There are about 400 plus herbariums. These are places where they scan these vouchers of plants that are flattened out, and even the UFA has one. 400 of them. If you're on the East Coast, almost all that data goes through the U of A, and it provides high-resolution image to millions of people. Okay? And so that brings me to something that's really close to my heart, which is democratizing innovation. We talked of open source, open data, platforms that put things together, but at the end of the day, innovating users often freely share their innovation with others, and they create what's called user innovation communities and rich intellectual commons. And I'll explain to you what that means for us. The person that is hurting the most, if you give them the right tools and the right training, the solution that they can build is vastly superior than some large organization coming and saying, here's the solution for you, please use it. We have thought of all possible ways. But the moment you give it to the user and they know how to make that change, they build something that's much, much, much more applicable to their question and to their community. And so CyberInfrastructure allows these freely shared innovations to be used by the community. Because if I took the algorithm, just like Stefan explained, and then put it out for use, but there's no place for you to run it, and there's no data for you to use, you end up not being able to use that innovation. We sort of solve that problem. So CyberInfrastructure is the glue that puts all of this together. And this book is free and open source. I would encourage you to read it. So far, we have talked of human, machines, and data, and even the platform. So now we sort of have an understanding of how all of these things come together. Let's talk of what the community is doing. So Here is improving agriculture. We all know 9 billion people. We have to feed them, and we have to get really efficient with our ability to grow things. There's a project called Genomes to Field, which uses our infrastructure. They want to develop corn that is very resilient to changing in environments. The important part is that they want to improve the ability to predict the crop performance as the environment changes. If you put the same seed in multiple locations, how the corn comes together is completely different. Even climates that are really close, Wisconsin and Minnesota, you will get completely different throughputs, output, performance from the same seed. And what they did is they gathered experts in genetics, genomics, plant physiology, agronomy, along with climatology and crop modeling, and with computation, informatics, statistics, and engineering. The reason I'm highlighting this is, if you remember that diagram, the circles far apart, this group realized that if we have to do something meaningful, we need that overlap. So they gathered the community. What did they want to do? If you want to understand how good your corn crop is, you take the cob, you take out the kernel, and you measure the width and the depth, okay? Sounds very easy. Remember the field biologists I told you? They are the people who will readily do something like this. If somebody like you or me had to do this, after about 10 kernels, I'm going to make mistakes, maybe eat some of them, drop some of them, lose some of that. And visualize trying to take a corn kernel and use a vernier. The vernier itself is painful, and now you have to do this. You're going to squish the kernel and then get wrong readings, and now it's like, oh my God, we damaged this kernel. And they have to do it for millions of corn kernel. Do you think there is a human being alive who will apply for this job? Okay? Unfortunately, we do subject some of our students to doing some of this, but not for millions, but okay? So the 2 dimensions of data, width and depth, okay? Well, remember the user innovation, okay? So when the group said, we are going to do this and we need to do it for millions, they went knocking on doors and said, who are the people who would know how to do this really fast? And so they went to the group in the University of Wisconsin. They have a crop innovation center. And in the center, what you can see is they're not roasting the cob on flame. It's actually a scanner, regular scanner, just like you would have at home for scanning photos. They just remove the lid, put a tape so that it thinks the lid is on, put a box, put in the corn kernels, put in the cobs, and just press a button and scan it. If they need to make the measurements right there, they just put the seeds, put the kernels on the scanner, cover it, press a button, it scans the image at high resolution. What happens next? So these are all the sites. You can imagine how many places are doing it. When they press that button and it scans, it all shows up in Cyverse. Once it shows up in Cyverse, it sends the data to Open Science Grid along with the analysis, and you literally get thousands, and I'm not joking. You'll get 4,000 or 5,000 computers simultaneously processing this data. So when you want to go through millions of these, Open Science Grid, remember open data, open software, Open Science Grid, this is where you can get analysis infrastructure at free. And then this processes all the data, and it converts data to information. Okay? Remember that pyramid. It took just scans, just images. We have no idea what's on it, puts all of that and creates it into information. And the team that takes all of that from data to information to knowledge is from Edgar Spalding's lab at University of Wisconsin. Nate Miller is a biomedical engineer who specializes in computer vision. He can take machine learning methods and apply that for machine vision. You give him a question and say, this is what I want to measure. He will literally put together, crafted with pride, with his own hands, an algorithm that will work beautifully for you. And you can just keep feeding images. So Nate did that. Celeste is the person that can then think of the questions about how the logistics work. And then Sarah, who's at the University of Missouri, when the data goes from data to information, Sarah has access to all the sites in Genomes to Field. She can pull in all the data, run the statistics, build the models, and say, you know, this thing works better when it grows in Arizona, but not as well when it's in Missouri. What we may have to do is if the weather model suggests that we're going to have warmer climate here, we should be swapping this and giving this to the farmers. So it's really interesting how this team together transforms data all the way to knowledge, and there's a lot of machine learning that happens in between. Here is open science. So everything that Nate built is available for the world to use. And this went from idea to usability in 2 years. Okay? So what happened? Here are the novel methods that produce novel data. On the left, you can see 3 types of kernel, 3 different shapes, and then it can easily categorize which kernel is what. And then on the right-hand side, you can see the cobs, and they couldn't even measure this before. All they could say is, oh, the kernel looks squiggly and very squiggly and little squiggly, but there was no explanation that was a mathematical explanation, a unit that they could put to the squiggliness, okay? And so by using these techniques, Nate gave them dimensions to their data, to the ability to now put that into clusters and understand what they had. So by just having those 2 measurements, they honestly were not making a dent in that analysis. And so now when you give these machine learning methods, remember what Stefan had said, the more data you give, more interesting things happen. And so now when you have these 2 dimensions, you can see the blue and the red. You still have to do that because the traditional scientist is going to say, where is the width and the depth? If I don't see that, I don't trust your data. I don't care about the shapes and the squiggly definitions. I need that. And so you give them their standard, and then you say, here's a lot more. Have fun. Okay? So what are we trying to scale here? Are we trying to make the networks fast, the algorithms smarter, improve the storage? I would say none of those. What we're trying here is to scale the Nates and the Edgars and the Sarah. Because when you empower Nate to do more, you allow people like Edgar, who is a plant biologist, but at the same time is so savvy with technology that he's had robots in his lab for more than a decade now. Okay? So Nate and Edgar are exactly in the center of that Venn diagram where they understand the technology, and the more we empower them, the more communities that they empower with their knowledge. And that sharing is what Cyverse is about for scaling. You can buy bigger hardware, you can buy faster networks, but if you have the right people, that's when you get the value out of all of that equipment. And so connecting the dots, remember the question of Santa Catalina? The awesome students in my class they actually built this, they gave it to the researcher, and now anybody in the US can go and take large swaths of the map and calculate solar radiation. Similarly, what Nate did is now used all over the world. Labs that wanted to do it, and the beautiful part is that they are all following the same standard. So without fighting with people, you now have a standard. Those of you sort of are in the academic area, then you know that the moment you have a standards discussion, it usually ends with a fist fight, because nobody thinks that what they do should be changed, and nobody agrees on a common standard. But when you start using common infrastructure, common data, suddenly those standards are very meaningful for you. Okay? So here are different communities, and each of them have their Nate. So what we've done is human data, machines plus Cyverse, we've given them a solution. So all of these groups, now you can see the Viromics and plant databases, teaching bioinformatics, they don't need help from us. This is completely on their own. They build their communities, they do awesome things. And so we've gone from a think tank where people would meet to talk about how will we do this to let's just do this and I know where to go. And that's an important part. So now I'm going to sort of come to the part where we talk of intelligence augmentation-driven innovation. What I've shown you so far is innovation. It does have the machine learning. It has a little bit of AI. But now I want to take it a step further and go into the IA and sort of give you a journey. So this is a slide from Mihai's talk, which says, intelligence augmentation. If we design machines to complement us, then we are free to emphasize features that are most useful without worrying how close we are to machines. If you remember the corn example, the number of dimensions of data that you could get, if you are allowed to design it and get the dimensions you need, and some that you didn't even need, you are now able to do things that you normally could not do before. But if we say, well, only 2 measurements, no more, you certainly start stopping innovation. Okay? So the intelligence augmentation comes in different flavors, and it's usually a slow process that comes through automation. And so here's a quote from Herbert Simon, which says, "The meaning of knowing has shifted from being able to remember and repeat to being able to find and use." So we are in the age of find and use. Okay? And for that, we need computational thinking. So Janet Wing in the early 90s sort of started explaining this concept to many people. This is not to think like a computer. You're not trying to be a computer. Rather, you're trying to think like a computer scientist. Okay? And what that means is when there's a question, you know how to abstract away from it and start thinking about it in layers. Okay? And if I take the example of the corn again, the person wanted measurements. If you start giving them, oh, you can just do this to get the 2 measurements you have, go away, then you're not really abstracting away from it. But the moment you start looking at it and say, maybe we should separate out the scanning in one way, the data goes another layer, the algorithms go in another layer, you now start thinking of the question in very different layers, and then you start thinking about automation. So those layers need to talk to each other. So you start sort of thinking of, how am I going to connect these layers? Maybe they should be speaking the same standard. Maybe they should be exchanging data the same way. And the reason you do that is, if there is a method that is really good today to find the boundaries in machine vision, tomorrow there will be a better method. Be assured that there'll be a better method. Are you able to just swap the old method out and put the new method in? Or are you going to reinvent the wheel from ground up? When you start using computational thinking, that abstraction, that automation, and that ability eventually gives you the audacity to ask bigger questions. In the case of the corn, you could say, can you now not do this with carrots? You have the same set of things. And the answer is yes. That's what Nate did, where he built that abstraction, where he said, this computation goes to open science grade. This data goes to Cyverse. This is what the users are going to do. And having those layers that can work well with each other is essential. And so using computational thinking is critical. I'm going to change gears on you and talk about knowledge capture. Many of my colleagues, and I remember in the early 90s, when I used to work very closely with them, they would look at an image and say, oh, this is this part of the plant, this is that. And I would ask them, how did you figure that out? And they would have a very elaborate explanation, which I think would take you decades of understanding. And now, those colleagues are retiring, they're going away. And if you look at this recent article from Nature, where the lost art of looking at plants, and it could be insect brains, be whatsoever, we have gone so much more towards genomics that the people who are looking at microscopy and looking at these images are fast fading away. And we have to figure out how to capture that knowledge. The beauty is that IA is going to allow us to do that. You heard from Mihai in deep learning, where you can train these models. Of course, looking at a cat and a panda is easy. Plant parts are a little bit harder. But these methods are now able to sit with an expert, where the expert cannot explain to you how they came to that point, but they're able to take it, and then you are now training models with that expert. So we are capturing the knowledge of these experts. So when they retire and go away, we are able to present the same image and say, what would John do? Or what would Leslie do? And how would she mark this up? And so it's really important that the IA part is respected and we capture this knowledge. Towards the end, I would say robot scientists, and these are not robots that are just doing automation. These are systems that you can give an hypothesis. If you remember what Mihai showed you, where there were millions of data points that his study produced, you can give it to this robot, and this robot will perform those experiments for you, not through just automation, but the experiments that fail, it's going to look at the images and figure out why it failed and what can be done to rescue it. You as a human don't have to. So it is doing that thinking for you so that you can focus on higher order. And so here is an example where neglected tropical disease. Nobody has time to work on this, and honestly, there's not much money to be made in pharma. So these are the robot scientists, when working together, are doing amazing things. And the example equivalent is a human and a computer together at chess can beat a lot more than just them independently. So what does it mean to work alongside thinking machines? Virtual associates, these are lawyers that you can take a legal brief and feed it to the system, and they will give you a deep analysis of the legal briefs. You can go to Case IQ and today upload a PDF. These are machine learning-based systems that are becoming your coworkers. So meet your new coworkers. These are all IA systems. Virtual residents, these are radiology reports that the image is already read before it hits the real radiologist, so that the radiologist is now just looking at measurements and performing much higher order tasks. Similarly, in your house, you have the virtual assistants and bots all around us. The important part is learning how to adopt and improve productivity. The key word here is improve productivity. Using these bots, using these assistants, will be a differentiator for jobs for the future. If you are not going to know how to extend them, how to engage with them, and how to be productive with them, most likely you're not going to be very much in the front line. But if you do, then that's going to be the job differentiator for you. And I would like to show you a small example of a virtual assistant that's doing some composing.
Having AI help speed up the creative process is interesting, but I wanted to know how Ava knows what to compose.
We sit down with the client, they tell us what they need. Is it an emotional song? Is it an uplifting song? And then they might tell us, okay, I need Ava to learn in the style of this specific composer, and maybe they need music in the style of Mozart or Beethoven. Every project is different. In NVIDIA's case, NVIDIA gave us some sample tracks, and we decided a subset of a database was similar to those tracks, so we retrained Ava.
So how did Ava learn to be a classical composer? It starts with a huge database of classical music that's stored in MIDI format. This means that the computer knows every note and chord that's played. It looks for patterns in the selected tracks to understand the basic style of the music. Ava practices by predicting what notes will come next in the track. Once it gets good at these predictions, it creates a set of rules for that style of music. It's now ready to create an original score. That sounds incredible.
And once the client is satisfied with the music, we're able to have humans orchestrate the piece, which means converting it from piano music to orchestra music, adding different instruments. And then once the client is happy, then we're able to record it with musicians.
1, 2, 3, et...
I was surprised at how emotional the music was. But that may be because there's still a lot of humans involved. Can AI really take it to the next level?
To judge music implies to be outside and to look from outside. And when I'm playing, when I'm conducting, whenever I'm conducting the music, I must be in the very heart of the music. But I think it's a big chance for creators and musicians to use technology in order to ask it to push us toward excellence.
So as you heard, humans are there, and this technology is going to push us towards excellence. And that is what we need to look forward to. And what you see here are my colleagues, my users, my collaborators, each of them being superstars, superheroes, and they work well together. And what happens here is that each of them have a role to play. You just have to know which superstar and superhero to work with. And finally, I would like to end by saying This is the proverb that I subscribe by. If you want to go fast, go alone. If you want to go far, you go together. And so we are in this journey together, and we want to go far. Come join us, be part of the fourth industrial revolution, and we'll have a good time. So thank you for the evening and being here.
Thank you very much, Nirav. And we'll see you all. Before you go away, Nirav goes to the point of academia where you ask a faculty member what's the worst problem that they have, and they say it's the status quo. And then the next thing that they'll say, and I hate change. Have a happy evening.
Thank you, everyone. And the train was on time.